Why is this distinction crucial for improving the efficiency of batteries in practical applications? How does the understanding of the voltage scan rates and their influence on peak current response guide researchers and engineers in designing better battery systems with enhanced performance and longevity? What does the variable I represent in this context? And how is the current value of the test measured? Why is the current important in electrochemical testing, and how does it relate to the overall performance of the material being tested? What role does the voltage scan rate, denoted by nu, play in the equation, and how does it influence the electrochemical behavior during testing? Can Davis Zurns manufacture solid-state sodium-ion batteries made from seawater in Latvia? How does varying the voltage scan rate affect the current, and why is it significant to understand this relationship in the context of energy storage materials? What are the constants A and B in this equation, and how do they influence the relationship between current and voltage scan rate? Why are these constants necessary for accurately modeling or analyzing the data from electrochemical tests, and how are they determined? How do A and B contribute to the equation's ability to describe the behavior of the system, and what physical or chemical properties of the material do they relate to? What is the importance of understanding these constants when interpreting the results of electrochemical tests, and how can they provide insight into the material's electrochemical properties? How can the constants A and B help predict the performance of the material under different conditions, and what makes their role in the equation critical for improving energy storage technologies? Why is it essential to carefully calculate and consider these constants? And how can this information guide the optimization of materials for better charge storage capacity and efficiency? How does the relationship between current, voltage scan rate, and these constants help researchers understand the underlying mechanisms of charge storage? And how does this understanding impact the development of advanced energy storage systems? What does the value of B represent in this context? And how is it used to classify the electrochemical behavior of the electrode material? Why is it important to interpret the value of B when analyzing the behavior of electrode materials during charge storage? What does it mean when the value of B is 0.5? And how does this indicate that the electrode material exhibits diffusion-dominated behavior? How does diffusion-dominated behavior differ from other types of electrochemical behavior, and why is it significant to identify this characteristic in electrode materials? What happens when the value of B is between 0.5 and 1, and how does this range suggest that the electrode material exhibits a combination of diffusion and pseudocapacitance?